Hi everyone, and welcome again to this Copernicus Marine Service training for ocean color data. As you know by now, my name is Silvia Pardo. I am an Earth observation scientist at Plymouth Marine Laboratory in Plymouth, United Kingdom, and I'm here today to help you explore some of the ocean color products that you can access through the Copernicus Marine Service catalog. This is part 3, the final part of a 3-part series on ocean color. So if you need to, please feel free to go back to part 1 in case you need a refresher on how to access the data, how to investigate the data structure, how to open, extract and plotting data. During this session, this last session, we will use Copernicus data to explore the optical variables distributed in the ocean color from satellite observation products. And in particular, in this exercise, we will look at different products acquired during the subaquatic volcanic eruption near El Hierro in the Canary Islands. And we'll try to find the optical signature of the eruption and the changing color of the surrounding waters. That's why this final part is called visualizing the El Hierro eruption using products for the Iberian-Biscay and Irish Sea region. Quick reminder that we are working in this great Jupyter notebook environment that allows us to execute Python code in real time. So as always, you can use the buttons on this top panel to save your changes, add some cells, copy, paste, cut the cells, and especially those two buttons, remember that they are the most important things when running code. So for running a code cell, a code box, you have only to press the play button in here, and if there's an issue with the code you're running, you can interrupt the execution by pressing the stop button up here. So before getting our hands into the actual optical data, let's try to understand a little bit more the physical principles behind ocean color, very briefly. So we kind of discussed this in part 1 already, briefly again, and we've said that water molecules absorb almost all sunlight, except for the blue part of the spectrum, which is reflected back. And this is the reason why open ocean regions, where the ocean is relatively barren, relatively empty, look deep blue from space. The presence of non-water molecules alters the behavior of sunlight as it penetrates the ocean surface. And in this figure, we have some examples of some water components that are not water molecules, but they are present in the ocean, such as dissolved organic matter, phytoplankton, and inorganic suspended materials. And the effect of this suspended and dissolved matter on light depends on how big the molecules are and how many of them we have and what they are made of. When light interacts with a molecule, two things can happen. So radiation can be absorbed as energy, so in here we have absorption, and radiation can bounce back, can scatter back. So this, for example, this line in here shows the backscattering of a line of radiation that has interacted with the inorganic suspended material. So the figure in here shows the different fates that light can suffer when it interacts with the ocean. And this means that a fraction of the altered sunlight eventually makes it back out of the water. So this is basically the piece of light that makes it out of the water. And this can be recorded using sensors on board satellites. And if we know how different substances alter sunlight, Then measuring the outer sunlight that leaves the ocean allows us to deduce what substances are present in the water and in what concentrations. So as we discussed in the previous exercise, we have phytoplankton, which contain chlorophyll, which is a pigment which absorbs mostly the blue portions of sunlight and less in the green portions of the sunlight. And we have focused on chlorophyll, phytoplankton chlorophyll, for the parts 1 and 2 of this ocean color training practical sessions. But for this final exercise, we will look for a different type of molecule. In particular, we will study different types of suspended inorganic matter. So suspended inorganic matter is particularly frequent in coastal areas and contributes to the ocean color in the green, yellow, and red parts of the spectrum. So that's a wide range of wavelengths where the suspended materials can be detected. Let's see a visual example of this water constituents. So this is a natural color image acquired on the 12th of November 2012 by the MODIS sensor on board the NASA Aqua satellite. And this has captured the Guadalquivir River mouth as it empties in the Gulf of Cadiz, which is basically, this is Portugal, and this is the south and west coast of Spain. So you can see that both the river and the river mouth appear in a light brown color. So this is the river mouth and this is the river going inland. And we can easily identify this as a mud type sediment, and we can study the shape of the sediment plume that is formed when the river deposits this sediment into the sea, and how persistent the plume is, how quickly it disperses, to measure, for example, currents in this regional sea. But so this is a fantastic example, but probably the most spectacular event that we will study in this exercise is this one. So this is the October 2011, March 2012 El Hierro subaquatic volcanic eruptions. So this occurs, so this is the Canary Islands in the Atlantic Ocean, and this in particular is the island of El Hierro. And there's a submarine volcano called the Tagoro, and starting in July 2011 they detected increased seismic activity. And then they detected an earthquake storm, around 400 minor tremors between the 20th and the 34th of July. And then on the 10th of October 2011, the earthquake changed the behavior and started to produce like a harmonic tremor, which marked the start of the first submarine eruption, approximately 2 kilometers to the south of the island over here. And then we saw that they saw a second eruption taking place in January 2012, and basically around early March 2012, the authorities of El Hierro declared that the eruption was over. So you can see this was an event that lasted in different stages for months, basically. And what we have here is a true color image acquired in November, and on the 9th of November 2011 by the MBSAT Medium Resolution Imaging Spectrometer, so that's MERIS for short. And the image illustrates how the volcanic eruption altered the color over here of the surrounding waters, and shows the plume that's reaching out from the southern shore of El Hierro. So this is our motivation for this exercise. So now we have set up our objectives and the fantastic, spectacular events that we are going to study. We can start coding. So as we did in the previous two parts, we will begin by setting up environment and data paths. And we will use the following libraries. Most of them you have already seen. There are two of them that might be new for you. The first one is the daytime, which haven't really been paying much attention to it so far, but the daytime module supplies classes for manipulating dates and times, including date and time arithmetics. So for example, adding a time delta to an existing date time object. And secondly, we have a new library, which is the CAR-to-P feature, which we are importing as C feature over here. This module contains functions that will allow us to define collection of points, lines, and polygons with easy methods for drawing and filtering. Once we have an environment is set up, we will define our optical dataset. So as we saw in the presentation, and I think I included a variable list also in the first exercise, the Copernicus Marine Service Ocean Color Thematic Assembly Center produces a variety of optical products. So we have remosance and reflectances, suspended matter concentration, particulate backscattering, transparency, so that's measured with the Secchi Depth, diffuse attenuation, and the absorption coefficients. And in this first section, we will be looking at remosance and reflectances, which provide critical information regarding the visible solar radiation reflecting from the ocean surface, and which is then detected by the ocean color sensors. While solar radiation can be seen as a continuous variable, it basically gets subsample at sensor level. This means that the remosance products are only available at certain wavelengths. So this in here, you have a list of the wavelengths that we have available within our dataset. And each of these bands is distributed on an individual file labeled with the corresponding band center wavelength. So basically the remosance and reflectance files for the band 443 nanometers is labeled as RRS 443. The spectral remosance and reflectances are also key, not only by themselves, but also key for ocean color retrieval of water by optical properties. In particular, many chlorophyll algorithms are purely based on ratios or differences between these remosance and reflectances at particular bands. To some extent, this is actually the case of the regional chlorophyll algorithm that we have used in the products that we have used for the first and second exercise. And without going into much detail, the chlorophyll algorithm is called OC5CI, and it's a combination of OC5, which is a 5-band empirical algorithm, and the color index algorithm, which is a 3-band reflectance difference algorithm. So our datasets, so the physical variables described by our datasets are quite different from those we use for exercise 1 or 2, but the naming convention, as you can see, is pretty similar. So we can easily identify that these files, for example, are global, are reprocessed, are level 3 data. They are being processed from different data streams coming from different sensors. The resolution is 4 kilometers, and the production unit is ACRI. Here, basically, we have then defined a list of relevant files for 3 bands corresponding to the 28th of October 2011. We will then load the files to create the datasets using the usual open dataset function within Xarray, and then we can save the latitude and the longitude variables, and we do this here to save some time, as we'll be saying for all the files in this first section. So basically what we have in here is a bunch of remosance and reflectances ready to be used. And so what can we do with them? So the first and easiest thing we can do with them is to map them, basically, the same as we did for the chlorophyll. But plotting a new variable can be tricky because we don't know anything about the value types and ranges. Is remosance and reflectance a linear variable or a log normal variable, as chlorophyll was? So to answer this question, we can explore the data structure as we did in previous exercises. You can happily try to do this here, and you can just pause the video and copy and paste some code from parts 1 and 2. But we can also, in the particular case of remosance and reflectances, we can try to look at the spectral characterizations of remosance and reflectances in the literature. So as with just discussing the introduction, the values of the remoteness and reflectances across the spectrum are dependent on the water constituents. So this figure in here summarizes typical remoteness in the spectra for different water types, as characterized by Jackson et al. In a paper that was written in 2017. So in general, you have 14 different water classes, and the spectra in the shape of water classes 1 to 7, so that's starting in the red, going into orange, yellow, and green, are obtained for clear open ocean waters. Whereas those shown in spectral lines similar to classes 11 to 14, so that's basically the blues, purples, and pinks, belong to more turbid coastal waters. So if we have information about the optical water type in our area, we can try to guess the variable limits when creating reflectance maps. So for example, remoteness and reflectances in the blue bands around 443 nanometers only reach values above 0.01 stereo radians to the -1 for the very blue oligotrophic waters, as one will be expect in the North Atlantic. So to understand how the different wavelengths and by extension the different water constituents contribute to the global ocean color, we will try to build a natural or RGB color map for the area. So this is a product that combines red, blue, and red, green, and blue image slices to be aggregated in a single image that seems kind of realistic to the eye. So for our example, we will be defining the color red with a band 670 nanometers. The color green will be represented by the band at center at 555 nanometers, and then we have the blue band, which we have chosen 443 and the 443 nanometer band to represent the blue color in our image. So in here, in this further down, following the execution of the different code boxes, we define the corresponding variables for the green and the red and the blue channels, and the syntax is exactly the same as we've been using for the whole workshop. So now we have these available, loaded. We can have a look at the three bands separately. So for example, let's create a map of the remoteness and reflectances in the blue at 443 nanometers. At this point, you already know everything about plotting, so I won't go through this code in detail, but there are two main differences between this plotting sequence and the one we use for chlorophyll data. First, we are no longer transforming the data array before plotting. So in here we are plotting the blue data stream straight away. The reason for that is, as we saw above in the water class figure, the range of typical values for remoteness and reflectances are quite small, are quite narrow. So remoteness and reflectances values don't go across several orders of magnitude as chlorophyll did. And the second difference is that we have used a new color map called Blues R, which is what we call a sequential color map. So in a sequential color map, the lightness value increases through the color map. And because we have, so that will be true for the blue color map, but because I have appended the letter R to the color map name, this means that the color map will be reversed. So this means that the lightness value will increase through the color map. Will decrease rather than increase through the color map. So this is the resulting remoteness and reflectance map from the daily product for, let me check the dates again. So that's the 26th of October 2011. So for this specific color map, the lighter the color, the larger the amount of blue light at 443 nanometers our sensor is detecting. But as you can see, for the area out of the south coast of El Hierro, we can't really detect any particular light areas in the map. So we can conclude maybe that the signature of the eruption is hardly visible at this wavelength. As we know, the pixels affected by cloud cover are masked out, but if we could see the clouds, they will appear white because they reflect lots of green, red, and blue light. So we kind of saw this effect in the true color images in here. And in the same way, if land areas were not masked in our data set in here, we will see that they reflect a lot of radiation in the green channel, because this channel is sensitive to terrestrial chlorophyll. So that's exactly what is happening in these areas in green in here. So we can try to compare this blue band, so for 3 nanometers, with the green and the red bands. So that's at 555 and 670 nanometers respectively, to see if the same is true across the spectrum. So this is the optical signature of the Hierro Eruption. So here we are plotting, we have the plotting sequence for the green band, 555 nanometers, which is identical to the plotting sequence above. The only difference is we have used another reverse sequential color map called greens, which works exactly the same as blue's color map, but uses a range of green tones basically. We can now visually compare this map with the above, and now the situation has changed a lot. But let's see further down another plotting sequence. So we have then the plotting sequence for band 670 nanometers, which is this one. And again, the plotting sequence is exactly the same as we've been using for the past 2000 plots, and is exactly identical as the one above, but with a different color map. In this case, we will be using red tones. So now that we have the 3 bands, we can compare the blue band, the red band, and the green one. And I think it's clear. I mean, we have to scroll up and down to visually compare these variables, but I think it's very clear that the effect of the eruption is way more visible in the green and in the red bands. So that's the signature over here, than in the blue. So this is due to the optical characteristics of the particles released during the eruption. We can now combine these 3 channels into an RGB image using the image show function, which should be somewhere here at the bottom. So this is a different use of the image show function than the one that we saw at the first exercise, and that we only had one variable that we had to, it was a 3-dimensional variable that we had to convert to a 2-dimensional variable. But here it's a bit different, so because we have 3 different data streams, one for the red, one for the green, one for the blue, which naturally describes an RGB model. As you might know, the RGB model is a color model in which red, green, and blue bands are added together in various ways to produce a final color, basically. And color in this RGB model is described by indicating how much of each of the red, green, and blue bands are included. So basically, an RGB value is a triplet. And then you have 3 components, one per one of the bands, and each one of those components can vary from 0 to a defined maximum, and that maximum usually is set to 1 for floating point variables or values such as the remote sensing reflectance. All this means that we will need to normalize our reflectance values to RGB values. So RGB values must be between 0 and 1. And we can perform this conversion by normalizing the 3 channels. That's dividing each one of the arrays by the sum of the 3 arrays, which is what we will be doing at some point in this command sequence in here. But first, we will subset the data to zoom in around the Canary Islands, around our region of interest. So we have seen this operation several times already. We identify the indexes inside the box. we convert the indexes from two-dimensional variables arrays to one-dimensional vectors. Then we extract the zoomed-in data from the original files. So that's the original red, green, and blue data sets, and also from the daily latitude and daily longitude. And then we can define, once that we have the zoom-in arrays, we can define the total RGB signal as the sum of the three channels, as we do here. And then we will normalize the reflectances, as we said, by dividing the value by the total signal. Here we are also using the Numpy clip function. So basically this discards everything that's outside the 0 to 1 range. So that's quite handy. Here we have some common code that shows you how to implement a gamma correction and for the data. This is applied to control the brightness and make the image, the final true color image look less dark. And this is not needed in this case, but I've left it in case you want to investigate it. Then here we can calculate a true green band from the other three from this. So this is the true green band that's calculated with this formula involving the red, the green, and the blue data streams. So this is not by no means essential for the exercise, but this takes into account that sometimes we need to work with sensors where the green channel doesn't really measure the visible green light, but it measures a near infrared band that's sensitive to chlorophyll-like things. And if we use that channel, which basically will be used the one as the input for the green stream, the green in our image appears too bright, too vibrant. So instead of using the G stream directly, we tune it down using this formula. Finally, once we have all our data sets, including the true green color, we can stack all the channels to create a three-dimensional RGB array. So we have seen the stack function in the past. This is another operation to convert pixels that have values that are not a number to numbers. So in this particular case, we are converting not a numbers to zeros, so they can show as part of the mask together with the land and the cloud in the final RGB image. And finally, we basically plot as usual. So we have a ton we define the empty map, we populate it, and basically this is the important instruction in here. We visualize the data using the image as show, which takes as an input the stacked RGB array that we have just built over there. So if we execute this long but very straightforward list of commands, we end up with this mapping here, which is kind of a bit coarse really, but provides relevant information about the types of water we see. So open waters are pictured in bright-ish blue. So in coastal areas are showing like a slight yellow tint, and in particular we have the subaquatic eruption showing very clearly in here, and this is the associated sediment discharge that appears in dark brown. So something as simple as aggregating data for three different bands tells us a lot about the optics of the water as well. To finish this subsection, let's see if I can find it. We will try to extract the reflectance spectrum from the area of south of El Hierro to see how the resultant spectral curves match the different water types we saw at the beginning. And to do this, for this first section in here, we will use the red band, that's 670 nanometers, to geolocate the eruption. So remember that the eruption was quite clear in here. So we will use values for this variable to geolocate the plume. And that's exactly what we are doing in here. Before we locate the plume, we just subset the data. So as usual, we identify the data array indexes for certain coordinate box, convert the two-dimensional arrays to one-dimensional vectors. But the exciting bit starts here. Here we define the eruption plume using the threshold on the red band. So the threshold we have selected is 0.0025 stereo radians to the -1. So as usual, we use the Numpy where section to do this kind of logical comparisons. And then we identify the locations where the red band, so that's the assumed red variable, is above the threshold, and we obtain the indexes, and we call those the eruption plume indexes. So once the plume is localized, we can define a list of wavelengths that we are going to extract, and we can initialize the array where we store the typical values for each one of those wavelengths as an empty array, an empty Numpy array with the same shape as the wavelength array. Then we will loop over the different wavelengths, as you can see here, extracting the plume volumes, calculating the median value as we go. So basically, we loop over the wavelengths using the variable W. For each W wavelength, we identify its position within the wavelength list. And so that's this instruction in here, and then we use that information to select the right file names and variable names. We then open the file that will load the variable, extracting the plume values. So we need to subset the data twice, one because we want to select a certain region, so that's what we are doing in here. We extract assumed then variable, and the second type of subsetting is to discard our remote sensing reflectance values outside the plume. So this is this second instruction here. Finally, we can calculate the median of the remote sensing reflectances, and we store this variable in the Hierro Eruption variable as well. And if we print the resulting Hierro Eruption variable, we end up with a spectra. So this is 5 different values, one per each of the wavelengths of the wavelength list. And we can see that the strongest signals are coming from bands at 555 and 490. We can easily do the same for other remote sensing reflectors and ranges that might define other water types. So, for example, still using the red band at 7670 nanometers as the reference, we can select the locations where the red bands are in the range between 0.001 and 0.0025 stereo radians to the -1. So these values usually correspond to coastal waters, and we do this in this line over here, and we store the results in the coastal indexes array. We then initialize a new empty array for the coastal extractions in the same shape as the wavelength list that we defined above. We loop exactly the same as we did before. We loop over the wavelengths, identifying the files, extracting and calculating the median. So we calculate the median in here. Here we are subsetting twice. So the only difference is that now we are discarding all the remote sensing reflectances that are not representative of coastal waters. So basically all those locations where the red band is below this number or above that number. And once we have the median for a certain wavelength, we can again store the value in the RS coastal array. And finally, we can print it using the usual print instruction. And we can see the strongest signals are still coming from the bands at 490 nanometers and 555 nanometers, but the average values from these bands are lower than those from the eruption plume spectra, which are here. And finally, in the same way, we can now use the blue band at 443 nanometers as the reference and extract pixels from the blue open ocean. So how we will define the open ocean waters. So those will be the locations where the remote sensing reflectances in the blue are higher than 0.01 stereo-radians, -1. We do that in that line here. And we, as always, we store the resulting locations in this open water indexes variable. We initialize a new empty remote sensing reflectance array, where we will store our medians for each one of the wavelengths. We loop over the wavelengths, extracting and calculating the median value of the coastal pixels. Ignoring not a number values that are not a number, as we did before. And we can finally print the resulting spectra from this RRS open water array. And you can see that the strongest signals are now coming from bands at 412 and 443 nanometers. So at this point, we have three spectra. We have mean remote sensing values per band for 3 regions: the eruption, the plume, the coastal waters, and then the open ocean. And then we can interpret them as spectral lines characteristic that characterize the very different processes that are going on in these regions. So to see this more clearly, we have this snippet of code in here. We have used all these functions already. So here basically we are using the plot function to plot the 3 different remote sensing arrays, which have a value for each one of these wavelengths in different colors. So the yellow represents the coastal waters, the red represents the volcanic eruption plume, and the blue represents the open waters. So as an exercise for you, you can now compare these plots here with the different water classes we saw above, and try to decide which class matches the open ocean pixels better, and the same for the coastal areas, and the same for the area that's affected by the volcanic eruption. So we are kind of approaching the end of the session, and in this last section we will have a deeper look at the optical signature, so that's going beyond the remote sensing reflectances. And to do this, we will be using the most sophisticated optical products in the catalog. So that's SPM, which is the suspended matter, SD, which is the Secchi Transparency Depth, and the Diffuse Attenuation, which is usually called KD 490. While this spectral sampling that we have just performed gives us a great idea of the character of the water masses that are present in this region, this analysis needs to be combined with other variables or with a full model of the in-water light field to be able to identify inorganic matter and to retrieve the actual concentration. For example, a measure of the concentration of SPM can be derived from chlorophyll and radiances at bands 555 and 7670. In the same way, the absorption and backscattering coefficients can be obtained from reflectances at some wavelengths, and then you can tune them using a semi-empirical algorithm to provide a measure of how quickly the solar radiation is diffused by seawater, and the resulting optical property product is called the diffuse attenuation. So let's have a closer look at these products. And down here we have listed the relevant files. So all of them, as the example above, were acquired during El Hierro Eruption. As we have been doing to the previous exercise, we start first with the list of the files, then we load these files to different Python variables using the open dataset function, and then finally we can save the variables. So here we are saving the daily latitude and longitude variables. We extract those from the KD 490 product. All those three have the same shape, so we don't have to repeat these two operations for the three variables. And then we extract the actual physical variables. So we will have first a look at the diffuse attenuation. So this is KD 490, which is a proxy for the turbidity of the water column. It's also related to the vertical visibility, which is analogous to the Secchi transparency depth, and the vertical visibility is inversely proportional to KD 490. So let's see what this product looks like during the El Hierro eruption. Here we have the plotting sequence, which is again identical to all the above except for the name of the color map, which will produce this pretty color scheme going from black to white using different blues and grays. As you can see above, not above, in here, the discharge of volcanic matter and fluids had a strong effect in water turbidity with values above 0.1 meters to the -1 inside the plume. So this is the volcanic eruption plume in here. This means that the concentration of particles, of scattering particles in the water column is very high, and light gets quickly diffused after it penetrates the sea surface, or in other words, there's suspended matter blocking the path of the solar radiation through the water column. So why is this important? Well, light availability, it is an important driver in the growth of many subaquatic organisms. So high turbidity events can be quite detrimental to the ecosystem. This particular coefficient, the diffuse attenuation coefficient, can be used to detect the extent of the plume, but also to give a measure of the eruption's intensity. And both the extent and the intensity allows us to compare the event with other eruptions. So the El Hierro eruption was really well studied by various research groups, and most of them, they conclude that the intensity of El Hierro plume was moderate. So the diffuse attenuation coefficient values barely exceeded 0.4 meters to the -1, and that only happened on a few specific dates. And they also described the extent, so the size of the plume. So they described this plume as stretching at its maximum 25 to 30 kilometers at the widest, and around like 100 kilometers long. So for the next step, we will use the usual way to select indices, the index selection tools, together with this diffuse attenuation product, to better define the boundaries of the plume and try to calculate the extent of the plume in kilometers, and we can compare these with the values from the literature. So if we scroll down to the actual code sequence, so as always, before we do anything, we subset the data. So in here we will be subsetting the data for the diffuse attenuation coefficient using this box. So that's from 27 to 28 degrees north and from 19 to 17 degrees west. We can then define the eruption plume. So we use a threshold over the diffuse attenuation product. So in this particular case, we're using 0.075 meters to the -1 as the threshold. So locations where the turbidity is above this value belong to the plume basically. We create an empty plume variable. We initialize that with zeros, and then we manually flag the pixels that belong to the plume, changing the values from 0 to 1. And finally, we can plot the extent of the plume as defined by this plume variable, which is here. As always, because the plume flag array only has two values, 0 and 1, it makes no sense to use a full color map, so instead we can build a discrete color map using two fixed colors. So in here, this is where we are defining our custom color field. In this particular case, we're using white and red, so the red will be denoting the volcanic eruption plume. And then, so we can use the usual plotting commands in here to obtain this kind of field, this kind of map of the extent of the plume. But we can also try to get a measure of the geographical extent of the plume in square kilometers. So we want to know what the area was. We can take advantage of the regularly spaced lat-long grid to derive the spacing between subsequent latitude or longitude elements. Then we will perform a really rough approximation to translate from coordinates to distances, so from degrees to kilometers. So the details are really beyond the scope of the session, but just to explain what each line does. Here we are converting, here we are making an approximation that says that 1 degree is roughly 111 kilometers for a certain region, which is kind of true for certain regions, not very far away from the equator. Here we are converting the latitude values from degrees to radians. Here we are building an array for the pixel widths in kilometers, and finally in here we are defining an array for pixel areas, so these pixel areas will be in square kilometers. And once we have our pixel area array, it's straightforward to calculate the extent of the plume. We can extract pixel areas values only for the values for the pixels that are inside the plume. Then we will only basically need to add them all to calculate the total plume area. And finally, we can use the Numpy array maximum function to get a rough measure of the intensity of the plume, and we will again select the locations in the zoomed in diffuse attenuation variable that belong to the plume and just calculates the maximum, and we print it. So all this, apart from the map, is resulting in a plume area of around 872 square kilometers and a maximum attenuation coefficient values of around 0.19 meters to the -1. At this stage, you can maybe take a short break, stop the video, and maybe go read the paper. One of the papers that I've linked in here regarding the observations done locally and not that locally of this volcanic eruption, and see if our results match those on the literature. So now that the plume has been clearly identified, we can have a look at the other optical variables. So the next one is the Secchi depth, which can be defined as the vertical depth at which a white opaque white disk, which is known as the Secchi disk, stops being visible from the surface. As we have mentioned a minute ago, the vertical visibility in the water column, which is the same as the Secchi depth, is inversely proportional to the turbidity or the diffuse attenuation coefficient. So let's have a look at how this product, so this is the Secchi depth product looks like during the Hierro eruption. identical plotting sequence, just using the Secchi Depth data set, and the only difference really is the color map, where we have used color map very similar to the blues, but here in green tones basically. As with turbidity, so this is the final map. The Secchi Depth is measured in meters. So the higher the Secchi Depth, the clearer the waters, the higher the transparency basically. So as with the turbidity, the underwater eruption caused a huge perturbation in water transparency. So Secchi Depth values are as low as 4 meters within the plume. So basically, putting the white Secchi Depth in the water, it disappears before it gets at 4 meters depth, which is a really, really short distance. In some cases, the Secchi Depth can also be interpreted as a proxy for the trophic state of a water mass. That means that being able to tell how productive a water mass is. So water quality indicators can be derived from it. So Secchi depths lower than 5 meters can indicate highly productive waters, with water quality falling to very low for values lower than 3 meters. So one could think the effects that the subaquatic underwater eruption had in the actual water quality in the area. And last but not least, we will have a look at the suspended particulate matter product. Once again, we have recycled most of the plotting sequence, but here we are using the SPM dataset with yet another new color map, which is called CVDs, which you can see here. And in general, this is kind of agrees with this SPM map we have obtained for the eruption date. The highest concentrations of SPM in the Atlantic Ocean are observed in coastal areas, so particularly in river mass. So we also have plumes, as we can see, associated with active submarine volcanoes that are also rich in SPM. And we can clearly see the signature in here, as we saw in the image of the turbidity. And this image actually, SPM reaches at points values above 3 grams per cubic meter within the plume. So that's really, really high. Because SPM contributes to water clarity through light absorption and scattering, its concentration determines the amount of light available for photosynthesis in the water column. So in other words, there's a significant relationship between chlorophyll and suspended particulate matter. So you might want to start thinking, after seeing this high concentration of SPM, on is there going to be more light or less light for a high concentration of SPM, and what are the consequences for chlorophyll in this area. So as a final exercise, I will actually suggest that you download the corresponding chlorophyll file for this date, and you build a map of the chlorophyll concentration to study the character of this relationship. So I think with this, we have actually reached the end of this Copernicus Marine Training for Ocean Color. And I really hope that you have enjoyed these practical sessions as much as I have enjoyed preparing them. I hope that these exercises have triggered a lot of questions and ideas, and it has been a great pleasure to help you explore some of the ocean color products you can access through the Copernicus Marine Service. Take care. Bye-bye.